Great. So, welcome again, everyone. So, if you completed the attendance form, I will share you our repository. So, yeah, I will share with you guys as well. So, try this QR code. It will take you to our GitHub repository. Zoom link. Are you on the Discord? Okay, go to the project workshop channel. You can find the Zoom link there if you want to join from the Zoom as well. So if you're at the repository, you can check our other workshops as well. So I will just quickly talk about them. So in the first workshop, we did facial expression recognition, where we built a PyTorch neural network model that was already trained, pre-built. And then we tested our model using facial expressions. And the second workshop was canceled due to the midterms and finals. And in the third workshop, we did histopathologic cancer detection, where we had these images, and each image has either tumor in it or not in it. So we basically looked at the images to conclude if an image has tumor. Sorry? Oh, sorry about that. There's actually 4 people waiting. Okay. Hello, newcomers. So let me share the link as well. Is the screen looking good? Oh, wait, I forgot to share my screen. Yeah. Thank you for reminding me. Alrighty. So what you can do now is go to workshop 4. And in workshop 4, we have one folder and a file. So I will first show you the folder. If you go to the folder, this is our basically data set. And we have 9 letters. And each letter has the corresponding hand gesture. So if you want to look one of the images, you can just click on it. Lagging a little bit. Then you can see like this is basically A. And you can look at the other images as well. We will look at them using code. And then here you can find the student handout. So download the student handout. And then we will use Google Cloud to work on the project. So first, download this. We need the link I will share. Yeah.
Hello.
So
Hi, what do we have to download?
I can send it on the Zoom chat as well. Let me do that actually. So you can download Zoom as well. So let me know if you have problems downloading. I always use terminal, so let me see if there's an easier way, actually. I always clone repository, but if you clone repository, it will take time because you will have to clone the images as well. Let me actually check that. Okay, so you click the row button. Let me go back. You click the row button here. And then you right click, and then you say save as. And you just save it like this. You can remove the TXT, I think. Yeah. So after doing that, you will have to go to Google Cloud.
I don't get the save as option.
If you download it from the Zoom, it should work as well. So I send it on the chat.
Yeah, I got it from the Zoom.
Yeah. So doing it from Zoom is easier, actually. Does everyone have the file? Yeah. We do it on Google Colab. You don't need a Google Colab. I just confused. Okay. You will just use Google Colab. Okay. And then you can choose the student handout from here or upload it from here. So I will just wait a couple of seconds for you to do that. And you say open the file. It uploads and creates a new file for you. Okay, so if you have any trouble coming to this section, let me know.
Recording in progress.
Has everyone done it? And are there any problems? Okay, if you had a problem, I will just send the link here and you can just copy this file. So I will start the workshop if everyone is okay. Did you guys manage to work? You don't download the images, I will show you. So don't download the images, I will show you how to do that. Okay, so let's start. As I said, today's topic is hand gestures recognition. And so this is Google Colab. If you have never used Google Colab, I will introduce that first. So this is our working place. And here you can see we have text and we have coding places. On the left, we have files. And as you can see, we don't have any files here. We just have sample data, but you can basically ignore that. So we will first do our imports. So let's run this first. And if you have any problems coming here, let me know. Yeah, Mingley also shared another tip to copy the the Python notebook. So let's run this first. If you click this button, it runs the code chunk here. And it's, yeah. Okay, so could you log on to the Zoom? I will share the link from there. Does anyone else have a problem? So log into Google Colab. I can show it here. Go here. Then this page comes up. Go to upload and choose a file from there. Yeah. So is everyone able to run the button here? Let me know in the chat if you click the button and it worked. Did it work for you guys?
Oh, you change the
Yeah.
take away the.
So what you can do is like just if you're on the Zoom, I will just send you the link. It will be the quickest, I think. So just copy this file. So we still have newcomers. I will send the attendance link here as well. And then the project link. So you get it. Sorry. Okay, when you click this link, go to file and then save a copy and then start working on that copy. So you just click save a copy in Drive. That's it. Done? Okay. So by now, everyone should be on this page. And then you first go to imports, click the button here, and then it imports everything. So I will just introduce what we are importing. So first we are importing OS to access the files we have. We import time to see how many minutes does it take to run the model. And then we import torch. So this is one of the most important things we import. PyTorch is the library we use to build our model. So PyTorch is basically one of the machine learning models along with other ones, but like it's one of the most commonly used, and it's mostly used in research and industry. So we will use this library, and then NumPy is the library used for math computations. Torch neural network is the one we will use to build our neural network. We will extend this library and then build our own neural network. I will show you that. TQDM is the library we use to show the progress, because running our model takes like a couple of minutes, sometimes hours. And you want to see like the progress of that. You want to see how much of it is done. TQDM allows us to see that. And then we have some other torch libraries. We have Matplotlib to visualize the data we have. And then we have Torch Vision to transform and prepare our data. So if you import all of these, at the end, you see we have git clone. So what does this do? At first, I showed you that our files was empty, but now we see 2022, 2023 projects workshop. So if you click on that, you can see we have project 4, workshop 4. And if you click on that, we have images. So all of these images are stored here. That's why you don't download the images. We just clone the repository. It's much faster. So can I get a confirmation in the chat if this worked for you? And did this work for you guys? Yeah,
Oh, you click-
you click this. You see the button here? Click on this. Do you see 2022, 2023? If you don't, did you click this button before? Click this button first. Yeah. Okay. Thanks for the confirmation, guys, on the chat.
The thing gets stored temporarily, like if you close the notebook and you open it again.
Let's test it. Yeah, let's test. This is a good question. Yeah, it stores permanently. Yeah.
Oh, it stores it if you connect it to your drive.
Yes, it needs internet connection. So it doesn't store it locally. Otherwise, that would be a trouble. So we will start off with data processing, pre-processing. So in each model that we build, data pre-processing is the most troublesome, but the most important part, because like most of the times the model we have won't be different than the models we have built before. But we have to prepare our data so that we can just put in our data into the model. That's why data pre-processing takes like 80% of the time that you are building a machine learning model. So the first code we provide is we just provided the code. So most of the part of the project we will code it ourselves. But this part is like this is not related to machine learning. We just use this to print the folder structure we have. And data loader, I can skip over this to be just like print structure. And data loader, I will just talk about it briefly. So why do we have a data loader? So let's look at the parameters we have. First is the data folder we have. So is it a train folder or a test folder? Determine this here. We have the class num. So it's a list contains number of sample sizes of each sign class. And a batch size is an integer representing number of samples per batch. So let's talk about what batch means. When you run your model trains on the images you have. But if it were to train images one by one, it will take forever. So batch size is basically how many images at a time it trains on. So if I set batch size equal to 32, at one iteration, it trains on 32 images. That way, it utilizes your GPU and CPU on your computer. It trains much faster. Otherwise, like it trains simultaneously on 32 images. If it were to set the batch size to the length of the images you have, it would not be efficient because then your computer would struggle. So you set batch size a small number, but it's a number good enough so that it like trains faster. So we will talk about batch size later. And it returns, so our data loader returns train loader, validation loader, and test loader. So if you don't know what these are, I will just quickly talk over them. So train data is the data we have to train our model. Our model trains on this data and it tries to be as perfect as possible, but not so much perfect because there's a problem we call overfitting. If your model trains on the training data and it has 100% accuracy, that means it's perfect for the data. But in the real world, it might not work perfectly because your data might be biased. That's why we have validation data. Validation data is a data we use to confirm our model is real world applicable. So our model trains on training data, confirms its performance on real world with validation data, and it tries to improve its size, improve its parameters, and at the end, it produces the best model it has. So it doesn't train on validation data, it just fixes itself. At the end, we have test data, and we use test data to confirm that the model actually is real world applicable. But after our test data, we don't train our model again. So we use the validation data to train our model again, but for test data, that's the final conclusion. So after emphasizing this, and we load data here, I will just move on to data visualizer. So this is a simple code again. So we will just use matplotlib here to plot images. So it will just get the image and the label. So label is the A, B, C, D, E, F, G, H, I. And we will just visualize that. So let me run this as well. Every code chunk you see, you have to run so that you can use the methods here. So if you have any questions about these methods, let me know. But this is like the unimportant part of the workshop. So let's start with visualizing our data first to get familiar with our data. So the first thing that we do is we call matplotlib and we say it inline. So in Python, in a normal Python project, you don't have to call this line. But since we're working on Collab, we don't want a new window to pop up. So we write this line of code so that it prints the images below. And if you don't know, matplotlib is a library we use to show images. And then we set the directory. So I set directory equals to, and then come here. Do you have any questions, guys? Yes. It's the person symbol. Percent, modulos. Yeah. Are there any other questions? Let me know in the chat if you do, or here. Okay, so we set a directory. So I could have just written the directory, but like there's an easier way to do that. So our directory is the image directory we have. I click the file button here, workshop, project for images. So I click the two dots I have on the right. I click copy path. Then I come here. First I do quotation marks and put the directory here. So this is a directory to my data set. And then we want to visualize the data structure we have. So I will just call the print folder structure. And I'll just put in the directory I have. I'll just wait for a couple of seconds for it to do that. Where is the directory? So to get the directory, you click here, copy path, and then you just, so let me erase this. After copying the path, I just paste it here. Does it make sense? All right, so moving on. And are there any problems, guys, or is everything okay? No, yeah. So matplotlib inline. So usually if you use matplotlib in your Python, it opens a new window and shows the image there. However, since we are working on Collab, we don't want to open a new window. We want to print images inline. So writing this line of code ensures that the image is right below the code. The files. All right, let me Okay, so moving on, I will talk about transformers. So let's write the code first, and I will explain what this actually means. So transform for this PyTorch transform. So let me write transforms dot compose. This allows me to do multiple transformations, and we'll put a list here. Sorry, close brackets. So the first transform I want to do is transforms dot tensor. Get rid of that. So to tensor basically transforms or image tensors. Tensors is, you can think of that as the, hold on, it echoes. So could you mute your mic? Someone, I think, forgot their microphone. Okay. So there's still an echo going on. So I will just mute people here. Okay. So tensor is the array that we are working with. It's a list of integers you can think of. So most of the machine learning libraries use tensors instead of lists and arrays because it's much faster to work with. So the first thing that we do is transform our images into tensors. Second, we want to normalize our images. So this allows our data to work more efficiently because normalization ensures your data is not biased to one feature. So someone's getting an error. Let me check. So you're getting the error because I think you forgot to run this line of code. So even though this code is provided to you, you have to first run the code. So click this button here if you have this error. So let's say we don't know what 0.5 is. So what you can do is click Command on Mac and Control on Windows, I think. And then you can see what normalize function actually is. So if you go here, we set the mean as 0.5. So each number is centered around 0.5. We set the standard deviation as 0.5 as well. And we set it as in place as well. I'm sorry, we set the mean as standard deviation. So this is the mean. Our data is three-dimensional. So can anyone tell me why or each pixel in our image has 3 dimensions? Does anyone know why? RGB, yes. So our data is RGB, which means each pixel has a red, an integer representing how red it is, how blue it is, and how green it is, how much green it is. So that's why our images, each pixel is three-dimensional. We set each pixel to be centered around 0.5, and we set each pixel and each color channel to have a standard deviation of 0.5. This ensures less bias while training the model. So there are other transformations that you can do. You can do horizontal flips, you can do rotations to prepare our training model to make it more real world applicable. But we'll just continue from this. And then after transforming our data, we will call the data folder. So image folder is again a method by PyTorch, and it allows us to use the batch size in advantage because we want to use our GPU as much as possible without frying our computer. So I will just set a directory here and then transform. So we will transform images on the way as well. And then train loader, val loader, test loader, all equal to data loader, data folder, count L, and 1. So as I explained before, we use data loader to prepare our train loader, val loader, and test loader. And now we want to visualize some data. So I will start off with our train loader. And let me set a title, let's say train visualizer. So this is for my training data. I'll do the same thing for my test data. So I'll just copy the code, right? Test visualizer, then run this code. I made a typo here, let me fix that. Okay, so I will keep the screen on here so that you can see the code. But basically, you can see I have in total about 7,500 images, and it's almost equal divided, which is a good thing. So it's almost always important to see how your data is divided. If your data is not divided equally, then there are some other transformations that you can do to ensure your training data and test data are divided equally. So we can see it's very almost equal. So it's not much problem. It's not much of a problem in this workshop. And we can see the data we have visualized below. So this is my train visualizer. This is my test visualizer. Let me come back up here and let me know if you have any problems visualizing the data we have. I will check the chat. Is everything working? Maybe you made a typo writing transform? You have any problems? Can I get a confirmation in the chat if you see the images? And if you have any problems, let me know. I will try to help. You can see images? Okay, that's great. All good? Okay. So is everything working for you guys? Any problems? Working? Okay. Let's start building our model. So how much of convolutional neural networks do you guys know? Is this your first time like learning about it, or do you guys have prior knowledge? Yeah. Okay. So let me show you an image of a CNN. So this is a general image of a neural network. A neural network has an input layer and an output layer. And between them, we have hidden layers. So each hidden layer tries to understand data. And we have different layers. We have max pool layers, normal pool layers, fully connected layers. All those layers, all the purpose they have is to understand the data and then output a prediction. So let's say my input layer is the first image we have here. So it enters our data as a list of integers, and then it goes through those layers. And at the end, the model outputs a prediction, which is maybe A, the letter A. In convolutional neural network, the layers you have are kind of different, and we will talk about those layers. So first, I will start off with writing, like initializing our data. So the first thing that you should notice is that, so this is our class for our model. And the first thing that you should notice is it's a subclass of nn.module. So if you're curious about what nn is, just click comments and then hit, do that. Okay, hit module. And on the right, it pops up. So you can, if you're curious, you can get to know more about it. And it also gives you some like examples of how to build your own model. So we will do something similar to this. So first thing we do, we call the superclass of our model, which is nn.module, and then erase this pass. We write this pass so that we can start working. So erase that, and then let's name our model first. Let's call it simple CNN. So just the name of our model, and then I will set the first convolution layer. So this is a layer provided by PyTorch. So every time I use PyTorch neural network capabilities, I start with NN and then I press dot. And then you can see the list of options you have. We have average pool, batch normalization, and all the other layers, convolution layers. So we have a lot of options. We will use the most common one first. We'll use convolution 2D. Let me set the dimensions. So straight and padding. So I don't want to get much into the convolution layers. If you want to learn more about it, you can go to the study sessions we have because it's a huge topic. And the point of this workshop is to make something working. So I will just continue from here. And then the next thing we do is we use the pool layer. So I will just set that to max pool. And here I will use 2D as well. I will set my max pool dimensions as 2 to 2. And let me set another convolution layer. I will call this home2. And it's basically similar to one we had above. So your pools have dimensions. So each convolution has dimension, and 2 to 2 is the dimension of your pool. So it looks at 4 pixels at one time. Basically. And then I will continue adding the dimensions and my stride. We set it as 2 padding. We don't set any padding here. And then we will add another pool. So be careful about naming your instance variables, because if you set 2 things with the same name, it will give you an error. So I will again call max pool. At the end, you will have fully connected layers. So as you can see, we did a very simple model. It has a convolution layer first. After that, we have a pool layer. After that, we have another convolution layer, and after that, we have another pool layer. We could go on with this for a longer time. We could have maybe 6 of these, but at the end, we mostly used fully connected layers. So you can use 1 fully connected layer or 2 connected layers. The point of fully connected layers is that, let me go back to the image. So here you see we have a lot of nodes, so about 10 nodes, but we want to have a prediction that ranges, that has 4 different possibilities. So how do you connect each of these to 4 different possibilities? Use fully connected layers. And that's the purpose of that. We use 2 of these because we don't want to go from very large number of nodes to 8 different possibilities or 9 different possibilities, 9 letters. We want to go slowly, so we first go to a higher dimension first. So we set the fully connected layer as linear model. And then we set another fully connected layer. And at the end, we only want 9 predictions. So this takes 6 times 6 times 10 inputs, outputs 32. And then this takes 32 and 9 outputs 9. Why do we output 9? Because we have 9 different possibilities. We have 9 letters. So this is how we initialize your model. And let me talk about forward as well. So forward is how you pass information. So if you look at their model, how do you go from input layer to hidden layer? So we set these values. Let me close this actually. We set these instance variables, and now we want to use them. How do we use them? We use them in forward. So of course we first set the pool. We use a ReLU function. So we have different functions actually. Let me show you them. Let me show them quickly. So this is basically how we want to pass the information you have. So again, if I get much more into this, it will get confusing and it will pass the 2 hours we have. So I will just quickly mention that ReLU is one of the fastest models because you can see how simple it is. If it's less than 0, just make it 0. And if it's greater than 0, just have a linear function. So ReLU is the fastest function you can have. And then here we will pass the convolution. So what we do is we have our input x. We make x pass through self-convolution, the first convolution layer we have. It goes through a ReLU function to change the values to make it more fit to our model. And then we make it pass through self.pool. So we are going through 2 layers at one time here. You could have divided this into 2 different lines of code, but I just made it so that it goes through layers at once. We will do the same thing. So I can just copy this, paste it here, but now we have different layers. So first our pool is pool 2, and our convolution is convolution 2. So we want to change the dimensions of our x. So again, I will not get into much technicalities of the dimensions. But we want to make it so that we can put it into fully connected layer. In order to do that, we change the dimensions. And then we make it pass through the SATCOM fully connected layer. And then at the end, we make it pass through another fully connected layer. That's the second one. And notice that at the end, we don't run the ReLU function because we want to get the final answer. And we just return x. Okay, this was a lot to take in. So let me know if you were able to write this code. And let me check my computer first. Over the weekend? No, are you confused? Are you lost? Do you want me to help? I'm just waiting to take your time typing. You can use a sigmoid function, but it's slower to compute. So ReLU function is the fastest to compute, and it gets the job done. So here, for this workshop, we use the ReLU function. Yeah. It depends. But ReLU function, used to not be ReLU function has become popular in the recent years. We used to use sigmoid function a lot in early 2000s, and then they realized ReLU function is enough, is adequate, and since it's much faster to compute, we started to use ReLU function much more often. But if you want to see the sigmoid function, so as you can see, we have to compute e to the power of negative x, which takes time. It's a very trivial time, but if you do it for a lot of inputs, it's important time. Whereas ReLU function is just a linear function, so it's as straight as like multiplying numbers. It's so straightforward. Like oh, yeah, you can do that as well. I think it's called. Oh yeah, you mean leaky? Yeah. Yeah, leaky ReLU is also used, but here we use ReLU. So for those who are wondering, we were talking about this function. So difference between leaky ReLU and ReLU is that instead of making it 0, if it's less than 0, it just makes it a negative number, but the slope is different. So this is all the technicalities. We don't have to talk about them that much. Let me go back to code. So can anyone tell me how many hidden layers we have? Take your time. Oh. So someone said 2. Let me get more opinions. 4. Okay. Someone just give me a number. 3. We're just talking about hidden layers now. So our input layer is X, our output layer is, again, we are returning X as well. But like, I'm talking about the hidden layers. So the layers in between. So let me show you the image. This is the input layer or X. Our output layer is one of the ladders. And how many input layers we have? So someone said 6, and 6 is the correct answer. Why? So our input X goes through convolutional layer first. That's the first layer it goes through. And then it goes through a max pool layer. It does this again, it goes through another convolutional layer, and it goes through a pool layer. So this is 4 hidden layers. At the end, it goes through a fully connected layer. The fully connected layer is also a hidden layer. And at the end, it goes through another fully connected layer to output a prediction. So if you go to this image, you can think of this as 6 hidden layers. First 2 is a convolutional layer plus a pool layer. The second 2 of them are again convolutional layer and another pool layer. And the last 2 are 2 fully connected layers. So that's the structure of our model. It's a rather simple one because we don't have a lot of convolutional layers. If you were to check out workshop 3, there we have more layers because that one was more complicated, our model. So there we sacrifice time to improve efficiency. And our forward is self-explanatory. We just like make X go through the layers we defined here. So X first goes through here, and then it goes through the full layer after going through the ReLU function, and it repeats this. So this is basically our model. After doing this, make sure you run the code chunk, and then if everyone were able to copy, I will continue. So someone says, isn't FC2 an output layer? So you can think of FC2 as this layer. So it's a hidden layer that sends data to the output layer. So in output layer, we just have 9 nodes. So it's kind of confusing. But let me know if you have questions. So let me. The output layer is the output, yeah. Exactly. FC2 connects to the output. Okay. It's nice that you guys are getting it. Yeah, it makes me happy. So we define the function here because like you don't need to write this. It's just the naming convention we have for our model. So we will talk more about this when we use this function. So I will just pass this now. And then our training function. So this is the function, guys. This will take time. So the training function is the function that we use to train our model on the training data set. So we created the model here, but we are not using the model. So let's use the model. Okay. I will delete pass here. So to start computing, to start writing. So I will set a manual seed. This ensures that I get the same outcome. You don't have to set this, but like if you want to get the same accuracy as me, so you can set this value. And then I will set a loss function. So loss function basically measures how far off you are from the truth. So our output predicts, let's say, A, but the real answer is B. You know that you are incorrect, but like how far are you? To measure that, our model actually doesn't really output A. It has some integer value in it, okay? So you can think of A as 0, B as 1, and let's say your output is... So actually, we have like 8 columns of integers. Okay, that's kind of confusing. Let me just say loss value is the function that measures how far are you, okay? So it's not just you are incorrect or correct. There is some integer value that measures how far you are. And let me show you the loss function if you're curious. So it's basically the actual response times the logarithm of your prediction. Okay, it's kind of confusing. I will just move on from here. You can just think of the loss function as how far you are from the truth. So we want our model to maximize this or minimize this. What do you guys think? Minimize, right? Loss function measures how far you are, and we want to minimize how far we are. So we measure our distance from the truth, and we want to minimize that. And that way, our model will train.
It's not like an array of, let's say if you have 26 letters, right?
Mhm.
Is it an array of, let's say, I'm 0.8 to A, 0.3 to B?
Yeah, you can think of it like that. You can think of it like that. And you want to be 0 away from A if the answer is A. If you want to be direct on that. So if you're 100% correct, loss function should be close to 0. And I'm saying close to 0, not perfectly 0, because your model doesn't output like A. It outputs a list of integers that represents A, but it's not exact A. It's closest to A. Okay, let's move on. Loss function is kind of confusing in higher dimensions. And we want to set an optimizer. So our optimizer is basically the algorithm that we use to minimize the loss function. And one of the most common optimizers is an ADAM function, but here we will use as stochastic gradient descent is similar to ADAM. And we will pass the model parameters here. And then we will set the learning rates. So learning rate is how fast your model learns. If you set it too fast, it passes the optimum value. So it might pass so if you can think of the loss function as a function that has a local minimum, okay? And you want to find this local minimum, the minimum loss value you can have. And the learning rate is how fast you approach the local minimum. If you approach too fast, you will overshoot the local minimum. And if you set it too slow, it will take ages to get to the local minimum. So you want to set the learning rate a good number so that it approaches in good steps. Like it's not too much, it's not too slow. And 0.01 is usually the number we use. You can use numbers around this number. Like you can also set 0.005. Well, 0.01 is okay. So we set the learning rate. LR represents learning rate. And then you set the momentum. which is kind of similar to learning rate. So we will define some lists. We will define iterations, epoch iterations. I will explain what these all are. Losses, validation loss, train accuracy, and validation accuracy. So these are all empty lists. We have 1, 2, 3, 4, 5, 6 empty lists. So 4, 5, and 6. I will wait for a second for the coffee. And then let's set n to be the number of iterations. You will define progress as the number of epochs times lengths of the train loader. So basically epochs are defined with batch sizes. So remember how I told you a batch size is how many images at a time our model learns. So let's say our model takes 64 images, which is one batch size. This is one epoch. If it takes another 64, that's 2 epochs. So epoch defines that. And then we use this to see the progress of our model. So the numbers we write here, the variables we define here, we use them to measure the progress of our model, because you want to see the progress of your model. You don't want to know, like, so if we didn't write this, we will just wait for 5 minutes without knowing the progress of our model. So we want to see that, obviously. So we will use a TQDM library to see the progress. And then let's give it a name, while loop. And total is the progress total. Let's update that twice. Then we want to measure how many minutes does it take to run the model. So time.time. So let's start with our training loop. For epoch in range num epochs, so as you can see, num epochs is defined in training. It's a parameter of our function. So here, for each epoch, we want to get the images and labels in our training loader. We want iterate over this, so we pass iterator, because otherwise the PyTorch data loader is not iterable. And then let's say so CUDA is, let me talk about CUDA. CUDA is something that we can use to run our model a bit. So if you don't use CUDA, your computer will use its own GPU and CPU, which is the hardware of our computer, right? So if we can access the CUDA with our internet connection, it will run faster, so it will not run locally. So if we can use CUDA and torch.CUDA is acceptable or available. Let me see. Available. Yeah. Then images is equal to the images.CUDA. This is just some details. And labels equals labels.CUDA. So this is if we can use the GPU usage. So we have what? Mm-hmm. I will look into that. Yeah, I don't know much about that. So out is the prediction of our model basically. So let's define out is, so we pass our model the image we have, and then we will define loss as the criterion. Labels. Labels are the actual truth, the actual label of our image. Out is our prediction, the model's prediction, and we pass these values to calculate the loss value, and then we do backward propagation to improve the parameters of our model. So now that we know the loss, we can use backward propagation. So we set some values to our parameters of our model. Let me go back to this. You can think of each node as weights. So each connection is a weight. Like how strong the connection is. Sometimes you want the connection to be weaker. Sometimes you want the connection to be stronger. But like you don't know how stronger you want it to be. When you do it, you start off with some random small values, close to zero values. Each connection is kind of close to each other. Then you output the value. Obviously, your output is very random. So you calculate the loss value, and then you start from here, from the output, you go back, and while going back, you change each of the connections. You strengthen some, you weaken some, so that the next loss value is lower, which makes you closer to the truth. That's the idea of backward propagation. So forward is when you pass the data forward, you output, you predict something, you calculate how wrong you are, you go back, change each connection, and then you output again. I hope that makes sense. Okay. And then we will step our optimizer. And then we will use zero grad. It takes a cleanup step for PyTorch. So zero grad is a cool trick. And remember our iterations. We want to append the number of iterations we have done. So we will just append n. And then it's a cleanup step for PyTorch. So it's a detail. And then we have losses list, and there we will append the loss value, but you can't really do this because loss is not really a float number. So what we can instead do is convert loss to float, and then divide it by batch size. Because the loss value is the total loss value of the images, and we have batch size images. So if batch size is 64, this loss value is the loss of the 64 images. So we just want to get the average of them. And then let me write some comments actually. So backwards propagation here. And include this. So see progress. And then now we will get the accuracy and compute accuracy. So we will get the prediction first again. So again, out is not a float actually. It's a different data format. So we will transform it to float like this. And then we will see how many times we are correct by using this trick. So since we don't have one prediction, we have, let's say if our batch size is 64, we have 64 predictions for 64 labels. So instead of iterating over them, one by one to see how many times we are correct. We will just use this, like we will use a torch features to calculate how many times we are correct. So if you're correct, the torch value will be 1. Otherwise, it will be 0. And if you get the sum of that, you will get the sum of how many times you are correct. And item will return the value. So let me define total as the images dot shape 0. This is the total number of images you have. And the total accuracy is basically how many times you are correct over the total. And the train accuracy is, we define train accuracy above as an empty list. So we will just append the training accuracy. See what the training data. So this was for training data. So we will use it to see the progress of our model with the training data. I will just wait for a couple of seconds. If you are lost, I shared the link here as well. And I just saw one question. What's the difference between images and labels? So image is the image we have. It's basically, let's say if image has 100 to 100 pixels, the image's torch is basically 100 times 100 times 3. It's basically the pixels of our image and the color channels of each image. So it's basically our training data. We train on the pixels of our image and the color channels of it. Labels, on the other hand, is the label of the image. So basically, if the image is like this means A. Oh, wait, here. This means A, and the label would be A. The image would be this, the label would be A. So it's the actual value of our image. It's the thing that we are trying to predict. So if you go to this link, does it show the updated code I have? Is it real time?
It's happening in every one of the layers. What's happening in the single layer?
Layers. Yeah. Yeah. So as I said, like this is, let me close this. We start off with random connections, right? Like everything is connected, but like the connection, the strength of the connection is random. So these connections allows us to output something. Okay, so you pass the information here, they go from here, when they output something, right? We have 9 outputs, but let's say we have 4 outputs. So let's say this output here is 0.9, this is 0.9. The above is 0.3, the one above is 0.0, the one above is 0.1. So what's the strongest connection? What's the strongest output? It's this one, right? So you predict the value of this node. And in this case, your output will be 3, right? If you start from 0, 0, 1, 2, 3, you will predict 3. And if we had 4 letters, that would correspond to D. What does this mean? You had an input image, and then along the hidden layers, because of the strength of the connections, the output value was 0.9. And what happens in the hidden layers? They are just numbers. So we have, let's say we have 0, we have 1 here, okay? This connection is, let's say, 2. So you don't actually multiply the numbers directly, but let's say your algorithm just multiplies numbers with the connection. So you would have 2 here. And then other connections also correlate with that, and then you will get a sum of those numbers. Then you output D. But let's say the actual answer is A. So you are off. How much are you off? If the actual answer is A, plus what's the like corresponding values? The first one will be 1, the others will be 0.0. Yeah. How many are, like how much are you off? You're off 0.9 here, 0.3 here. You are not off there in the second one. And for the first one, you are off by 0.9 again in the other direction. Yeah, negative 0. So that's the loss value. If you calculate only accuracy, you will know that you are wrong, but you also want to know how much are you wrong. Yeah. So that's the loss value. After calculating loss value, you see that, oh, okay, by having this input, I should change my connections so that strongest connections lead to the first one for that specific input and for inputs like that. Yeah. So you go back, change the connections. You change the connections here, 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 and here, so that it's closer to the actual value. Does it make sense? Yes. I try to explain as like briefly as possible. It's a huge topic, and yeah, I hope that made sense. Yeah. Let me see if I have any questions in the Zoom chat. Okay. Yeah.
What's the difference between loss and accuracy?
Yeah, so let me explain that again. Let me draw actually. So you output something, right? You have 4 outputs here, yeah? So for this output, let's say you got 0.1. You said 0.0 here. That's your output for each node. 0.3 and 0.9 here, okay? So let's say each of these corresponds to A, B, C, D, yeah? So what's the highest number? It's 0.9, yeah? So your model predicts this and says, I'm predicting D. But let's say the actual answer is A, okay? So your accuracy for this model, like if you have 1 image, your accuracy is 0 because for that 1 image you are wrong. But what's your loss value? So loss value. So what's the actual matrix that corresponds to A? It is. Let me create a matrix here. It's 1 for the first one, for the first node, yeah. 0 for the second, 0 for the third, and 0 for the fourth. So this is the actual array representation of A. And this is your actual input. Your actual input is 0.1, 0.0, 0.0, 0.9. So you can calculate the loss value. So there are variations of loss value functions. Let's talk about a simple one. So you're off by 0.9 here, right? So your loss value 0.9 plus. For the second one, you are not off at all, right? You predicted 0.0, the actual answer is 0, so you're not off. For the third one, you predicted 0.3, so you're off by 0.3. And for the fourth one, you're off by 0.9. So this is your loss value. You want to minimize this loss value. How do you minimize it? You decrease the number here and you increase the number here for that input, for inputs similar to this input, right? So since we have 4 different outputs, our array consists of 4 different elements. So you can't just say your output is A. You want to like mathematically represent A. How do you represent A? This row corresponds to A row. This is B row. This is C row. And this is D row. So each row represents the letters. What's your output? Your output says, it's most likely D, right? Your output says that. Like, I'm with 90% confidence, I'm saying it's D. Like you can interpret it like that. So you can calculate the loss value like this. Does that make sense, guys?
So accuracy for each piece of data, like every single data you pass to the model is either 100.
Exactly.
Okay, and then you compute the average. Yes.
Yeah. For the accuracy, you can do that. So use the accuracy as a human to see how correct it is. Use the loss value as a computer to see how far you are off from the truth. That's why both are important. Yeah. 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 There are a lot of loss value functions. Like they are not much different from others. So I just stick to one and I use it. It doesn't matter that much. Like for simple problems, the architecture of your model doesn't matter that much as well. But for like high level applications, let's say a chess model, a neural network that trains on chess positions, architecture matters a lot. But that's beyond the scope of our workshop. No, thank you for your comments. We are not done yet though. Let's continue. That was the accuracy of our training data. So let's continue from here. So we want to increase n number of iterations. And then we want to update the progress bar by 1. So this was inside the inner loop, outside the inner loop, but inside the outer loop. Let me write that. Outside the inner loop, inside the outer loop. So that you don't get confused. We reset some values. To be used by the validation set. So for each epoch, we trained our images, and for each training we have done, we also want to confirm our results with the validation set. So for validation images and validation labels in validation loader, it's kind of similar to the training set, but so let me show you. Let me write it again. So we repeat some code. So if use CUDA and CUDA is available. And then we will just use val images equals val images.CUDA. So we will get the images as interpreted from the CUDA, and same for the labels. And then we again output the model's interpretation of the image. We will predict Okay, so I did a mistake above here. So if you guys could go to this line, at the end of this line, I should have said this. So at this place, otherwise you will get an error. So I did the change. Let's fix that. And then I will write a very similar line of codes. Val labels. That's view as spread.
are we using a local GPU to run the model?
We will try to use CUDA. If we can't use CUDA, if CUDA is not available, we will use a local GPU and CPU. This is correct plus or equals, so I changed this as well. We're just basically doing the same thing for validation. I'll just wait for a couple of seconds for it to copy. This is like identical to the training loop. Also, you can use this link if you're lost. I think it should show. Let's try. Yeah, it doesn't show the changes. Okay. Never mind then. Okay. So this is the validation loop. And end time equals time at time. So outside the validation loop and outside the outer loop as well. Now we first look at the accuracy of our validation, sorry. So we will first define V accuracy and V loss as the, or let me do it in separate lines. V accuracy is the correct over total and V loss as the loss value divided by total. And then I will add this to my arrays, the list that I defined above, if you remember. I'll add each of them.
Happy balance.
Yeah, man. I would increase the epoch iteration. So this basically saves the progress. So what we wrote here saves the progress, but we also want to save our model. So to save our model, we will write this. We will first define where we are setting the model. So get model name. This is a function that we previously wrote. So we first pass the name of the model. We pass the batch size of our model. We pass the learning rate of our model, and we pass the epoch. So that's the convention that we use for this workshop. And then you can use PyTorch function torque.save to save the model. So we will save the state of the model, and then we will save it at the path that we have previously defined. Okay, that was our loop. So let's exit the loop. Let's look at the end time. Time. And let's look at how much time it has passed. And time minus start time. And then we will just print total time elapsed. Up to 2 decimals. And we want to plot. So we want to plot the progress. The progress is defined by your training accuracy, your training loss, and your validation accuracy and validation loss. So we want to plot those as graphs. The way we can use this, we do this is basically using matplotlib as well. So plotting, training, loss versus validation loss, and validation training accuracy versus validation accuracy. So plot that title training curve. Let's say plot iterations, losses, and label equal train. And then we will plot epoch iterations, validation loss, and label validation. Plot X label iterations. Yes, outside the validation loop, inside the outside epoch loop. Does it help? Just well. So this is inside the epoch loop. This is outside the epoch. Okay, thank you. And plot that y label loss. Plot that show. This will print the loss. Let me change title. I will just copy this, paste it here. And we will look at the accuracy here. So instead of losses, we look at train accuracy. Instead of validation loss, we look at validation accuracy. And our X label will stay the same, but our Y label will be accuracy. I will add a legend here, so that's legends log equals past. And then finally, final training accuracy. Format, train accuracy, and the last element of that. And then validation accuracy. Okay, let me run this. I expect a lot of errors because of the typos I made, but we will solve these errors one by one. So let's try. Oh, first okay, that was our function. So now we will call this function. So I will just wait for few seconds, but note that I most probably have errors here. So we will call this function, probably we will get an error, and then we will fix it. So I will just wait for a couple of seconds for you to copy this, and then I will come back to this after we fix it. So I won't spend much time here waiting here. So know that we will come back. While waiting, I will explain the plotting part. So we first set, so we plot two different plots. The first one is titled training curve of loss. So we will compare the loss value of our training function and the loss value of our validation function, validation set. So how do you do that? If we will plot on the same plot. How do we do that? We will call the plot function twice. The first one is iterations, and so the x-axis is iterations, the y-axis is the losses. The second one, the first one, the x-axis is the epoch iteration, the y-axis is the validation loss. And then we will label this. And then we want to plot this one. And the second one is quite similar. We just plot the accuracy. And for that, we just use training accuracy and validation accuracy. At the end, we will print the final training accuracy and the validation accuracy. But know that the final model you have might not be the best model you have. Maybe you had a better model, but while trying to improve, it was worsened. So oftentimes the final model is not the best model, but it is quite close to the best model. Just know that. You will see that when we print the plots. So let me just continue from here. So someone asked, what's the meaning of validation? Our model trains on training data. I mean, we quantify how real world applicable it is using the validation data. So let me show you the image here again. Remember the connections we had? Remember like how we set the strength of these connections? We do that using the training data. So these connections are set. With our loss data, we don't change the connections. We just look at like these connections, how true our model is with the validation data. And after that, we change the connections accordingly. So we version some connections to make it fit more to the real world data and fit less to training data. So this is biased, right? We change the model according to the validation. So how do we know our model is actually real world applicable? We do that using the test data. So that's why we have three different data. So we have one big data divided into three parts, and we need test data separately because we want to have a model. We want to have a data set that doesn't change the model. Because if we change the model after your training set, we don't know if it's real world applicable. That's why we keep a separate training set. And that's the purpose of validationing. Yeah, I hope that helps. So let me proceed from here. Let's train the model. I will set the directory. So I will get the directory from here again, copy path, and then paste it here. So let me print some blocks so that we can clearly see. And between this, I will get the print folder structure, directory. So we repeat the steps we had before. Not that it's necessary, but to see the data. And then go back up. Yeah, actually, we don't need to do this. Okay. I don't think we need to do this. Let's try this. I'll just define run CNN here. We will get our neural network model. We will get the batch size. We will get the number of epochs, learning rates. So here we set the learning rate to 0.05 because while I was testing the model, the learning rate of 0.01 was too small. The model was training too slow. That's why I changed it to 0.05. Like you can change it yourself as well. Then we will try to use a CUDA and we will see if it works, but I doubt it. So data folder equals image folder directory transform train loader, val loader, test loader, data loader. We will load each of these data from a data folder, count L, batch size equals PS. So let's try to use CUDA. If CUDA is available, we will use GPU. Otherwise, we will have to use CPU. And train and models, train loader, val loader, learning rates equals LR, batch size equals BS, and a num epochs equals. All right, let's see. Let's run this.
I think you have two items, LR, the learning rate, and the batch size. Learning rate, and then just did under.
Oh, here.
And then batch size. Yes.
Thank you. Let's see. Okay, this function also seems to be working. Let's actually run this. So I again want to print inline. So the moment of truth. And let's set CUDA to true. So this will run our CNN model with training data and the validation data. But let's see if it actually works. I'm expecting errors, guys, so don't be surprised. Let's see. Okay, yeah. I noticed that when I was writing the code, so I come back up here. Here I said CUDA underscore is available. Instead of underscore, this should be dot available. And I did that twice, I think. Yep, here it should be dot available. So after changing that, I can come back down. Let's see. I did that again. Okay, how many times did I do it?
You just have to improve the brackets.
No, it's just I said underscore available.
There, I think you can.
Which one?
Yeah, dot is available.
Yep. So after changing something, you have to run the code again, guys. I forget that, so let me come back down. It is working. All right. That seems to be the only error. Let's see. Epoch iteration. Let me see that. So I said epoch iterate here. So let me change that. Okay. Before running our code, actually, I would create another folder here. I will call it models so that we can save our models under here. So after changing my code, I run this code chunk again. I come back down. I run this. Let's see. Why is it giving the same error? Okay. It seems that I have inconsistency with writing epoch, so yeah. All right, let's try this. The epoch error should be resolved. So you might have another error, so let's see. If you make it to the 4%, then we should go around. All right, it seems to be going good.
If you scroll back up to the train function.
Not this one, right? This one.
A little bit.
Up? Yeah. I will scroll back down to see if it's still working. Okay. It doesn't save the models though, I think. Okay, it's saving the models. That's nice. Okay. It's not saving inside this for some reason. Like we ideally wanted to save it inside the models folder. So not have like this looks kind of ugly because we will have a lot of models, but like we can fix that error later. It's a minor error. It's an error. So we are waiting for the model to train. I expect it to take like 5 minutes. After that, we will test it with our taste data. While waiting, I will take any questions. So this is a perfect time to ask questions.
Yeah, like if you wanted to make a CNN for language here, it would be exactly the same. And it's- Or
They will have a different CNN model. So
every month. Because I'm saying, why would you ever need to, I'm assuming the big tech companies have the best possible architecture.
Yeah.
Mhm. So if you're working at a data science job, you wouldn't really be making this from scratch, just be taking their one and working.
probably, but like if you're the first one there, if you're the first data scientist there, then you would have to like build your own model. But I don't expect it to be much different than the model. Yeah. So like we have a lot of different choices here, but actually you don't have much choice because there are some traditional models, and then you can like how do you know which model fits best to your project? Trial and error. You try that model, like you try to add more layers to it, add more hidden layers. You see if it works better by testing it on your test set, and after that you will conclude whether like which model works best. Or like this model we have, it's a very simple one, but although simple, it works. It gets the job done for this simple project. Let's say like if you're building a chess model again, chess is so complicated. This model would not be best. So you would need more hidden layers for you. The more hidden layers you have, the stronger your model will be, but the more time it will take to train. The more hidden layers may also cause like overfitting problems, but people not getting them.
If you wanted to make like easy chess one, would you purposely make it bad? Just so that you can.
Yes, exactly that. You would make the model bad. So I will share the source code after the workshop. I will share the recording as well. Don't worry about that. Let's see the progress. So 4 more minutes. It's slower than usual because I'm recording at the same time. So I can take another question, or like if you're having errors, I can help you with that. If you want me to scroll up, let me know. I can take any questions. Yeah.
How long did it take you to completely understand all this code?
There's this very cool PyTorch video on YouTube. I think it's like 6 hours long. Just write PyTorch tutorial, I think. Yeah. Choose the one with the most view count.
That was a long taken.
Yeah.
When you input the image, it takes the RGB to gray, it's just like one.
Exactly.
How does the computer like know that it's?
So this one line of code we wrote here transforms to tensor. It takes the image, it converts it to tensor. And tensor is basically like an array that you use for image recall. So this one line of code does all of that. That's why libraries are beautiful. Yeah.
Can you just say like general code to like doing other types of analysis like on like data instead of like picture? Like if I want to
Yeah.
analyze how people feel about something.
Yeah, that's the first. That was the first version. Yeah, facial expression.
Is that recorded?
Was that one?
Is it recorded?
It was recorded. Yeah, it's on YouTube. Yeah, it's on.
You know how the basic architecture is seen.
This is like a basic architecture. Like Could you repeat that question?
How did the basic architecture of the model?
Oh, sorry, current neural networks.
That's for second.
Yeah. It's time sensitive, exactly. So our CNNs are not time sensitive at all. We just pass the information from our NNs are time sensitive. So
What the
I can show you a picture. Yeah, all audios as well. Yeah. It's audios is the most common example for NNs.
Do one first.
Architecture.
Mm-hmm.
Like what part of that, like the layer thing would the better architecture include?
So this is architecture we have defined. A different architecture would be maybe adding another convolutional pool layer.
Like the physical hardware.
All physical. Yeah, I don't do physical. 83%. Okay. Only 1 minute left. Do you guys want a homework?
Yes.
Yes. Okay. So I have homework to you guys and guys on the Zoom as well. We have saved every model, right? And each model, like if you look at them, maybe you can see like what epoch it is. And we said that the last model, which is the model with the highest epoch, is like good enough, but it might not be the best model you have. So homework to you, save the best model. How do you do that? Look at the validation and look at the training accuracy and loss values. So maybe like choose between loss and accuracy, like which one would you prefer while choosing the best one? And then after choosing that, choose if you want to look at the training data, if you want to look at the validation data, if you want to look at both. And then by comparing models, only save the best model. So instead of saving everything. That's the homework to you guys. Take your time. Yeah, so this is an example of a supervised training. Why? Each of my data set is labeled. So I know this means A, right? This is supervised learning. Unsupervised learning, chess. I don't know if given a position, like I can say maybe white is winning, black is winning. But if I want to train a good model, I wouldn't say any side is winning. I will just give the position to the model, and I will let model do its thing. Then how would model know in that position which side is winning? The model will try every outcome and will try to see if there is a force winning by one side. If white is winning by force, then it goes back to that position and says in this position, white is winning. This is an example of an unsupervised learning.
There's no label.
There is no labels at all. Yeah.
This one does not have labels, or this one does.
This one does. The chess example doesn't. So we had another error. Name plot. Yeah, such a simple error. Okay. Let me get this. I will just copy this. And another code. Oh, man. Yeah, just for each report creates a new model. In this example we did, you don't have to do that. Yeah.
So it's invalid.
I will look into that. Let me finish this because we are kind of over time. So while plotting, I had an error. So I will just open this one to show you the images because the image is interesting. Now we'll go back to the code. I fixed the error there, but if I rerun the code, it will take another 10 minutes. So we saved the model, but we missed the images. So let me go back. So this is the image we get. The one on the top is the loss value. The one below is the accuracy value. So as you can see, as time passes, loss value decreases because that's the purpose of our model. We want to back propagate and improve our model. And if we increase the loss value, you can see it's correlated with the accuracy. Accuracy increases. Let's look in more detail. You can see the last iteration is not the best. It's close to the best, but like maybe this is lower than that, you know? You want to say the best one. And if you go here, this point here is greater than here. So the last model is closer to the best, but the best model is always like in between. So this is accuracy of the validation. You can see the training accuracy is like 95% or like 100% almost. And validation accuracy is 90%. It's a good number, but what's the test accuracy, right? We want to test our model. So I will go back to the original code. Even though there's an error, we saved the best model. So I'm just going back down. Let's test the model, yeah. So this is a very quick thing. I will just quickly write it since we're over time. Okay. So I will just get the data folder again. And I will get directory, transform, equals transform. And then I will get the train loader here. Cell. And then, yeah, I will get this line of code quickly. I will set the batch size as 128. I will create my simple CNN. Now we are doing something new. We have already trained our model, right? And we saved our model. So we will use our models. So this is provided by PyTorch. Load, state, dict. So we will use torch.load. And I will use the last model we have. And the homework to you is finding the best model and use that. I will copy the path, paste it here. So let me run this. So we uploaded the best, close to best model. And then for test images, test labels in test loader, output is equal to the output of our image, output of our model given the image. And the prediction is equal to, this is the same thing we have written before. So remember I showed you then like we wrote some things here and we said like 0.3, 0.0, 0.1, 0.9, and we get the max value to choose our prediction, right? This is what this line of code does actually. It looks at the array, it takes the max value, and then converts it to the letter. Right, this is actually converted to letter because the test label is also in numbers actually. So correct is equal to prediction that equal to test labels that view as prediction. And outside that, we get the sum of that and we get right. Outside the loop, we set the test accuracy as a correct over total. And then finally, we print the test accuracy. All right, moment of truth. How accurate our model is. Let's see. Oh, wait. %87%. Do you guys think it's a good number? Like for 9 different possibilities, we get 87. If we were to randomly guess, it would be 11%. So compared to 11%, 87 is a good number, I would say.
Why does machine learning make like? Because I wish that makes connection, but like each like guess is so random, right? So I increase accuracy by that much.
So
Why does it work? Like then like it just makes these connections.
Yeah.
Just
yeah,
so especially about these. Like, I know the connections were
Yeah.
meant to decrease the loss, right?
Yeah.
I'm just understanding like, oh yeah, this connection, right? Like how is it making that first connection?
it's interesting, right? So the way it makes those connections is that like it's just with random connections. Like everything is connected, but the strength of that is random. And then so it looks at the pixels, right? So for those sets of pixels, for those values, it outputs something and it knows how wrong it is. And it changes each connection to each output accordingly. So it says, oh wait, my A value is low. Let me make those connections stronger. So I will output a stronger value for A. For others, I will weaken the connections because I want them to be weaker. So it changes its values in the hidden layers as well. So that if you input a similar image, by similar I mean like sets of pixels with similar values, it will output a very similar thing. So it's not understanding anything. That's why we are doing transformations. Like I did some simple transformations, but you can do some transformations where you rotate the image, flip the image, make the image bad, like so that it's real world applicable. So there are some other transformations as well. At the end, we got almost 88%. So if I were to like choose so this was epoch 29, right? Let me try epoch 28. So this was 87.9. Let me run this with epoch 28. So 85. So it really changes. Yeah, that's the homework. I mean, it will be very similar to the line of code we wrote above, right?
Always the last epoch will be the best model.
Yeah, so you would assume so, but like if you look at this, so if you look at the training accuracy, like the accuracy, and if you look at the validation, you can see that like maybe this point here is greater than the end one. The one at the end, yeah. So it's not necessarily the last one, but the last one is close enough. You know, it's always close enough. But it might not be the best.
Why would they get it first? It's the same data. Why would your accuracy go down? I don't think it.
Because the way machine learning works is like you ask something, it's output something, and you say no, you are wrong by this, so it changes itself, right? Sometimes changing itself is the best thing you can do in the short run. Like the long run, it's always like you try to get as close as possible. It changes its connections. But like since like if you were to talk about training set like always kind of seems to increase its fluctuations. Well, validation set, it might depend because it's different data set.
Can you adjust how much the weights changes across, well, let's say
Mhm.
3 equals, then maybe the
That's the learning rate we set. You set it as 0.01, right? That's like how much you change. If you set learning rate as slow, as a very small number, it changes very slowly. If you set it as too big, it changes dramatically.
You said unsupervised learning doesn't have labels, so how does it compute those?
So it really depends on the problem you are facing. As in the test example, you are given a position, you didn't give any label to it, so you don't know which side is winning. But the neural network has to know which side is winning so that it can change, right? So it can try every possible combinations. And if one side is winning by force, let's say white is winning by force, like it goes back to that position and it says in this position, white is winning because there's a set of combination of moves white and black can make, which will lead to white winning all the time. So that's one example of unsupervised learning. There are different ways of calculating the loss.
What about if you get a cluster instead of learning? So in this case, if you want to cluster it into 9 different hand gestures, how do you do it?
In this example,
But without labels. You just want to classify it into 9 different types.
yeah, without labels, I can't think of an example. But yeah. Like unsupervised learning is all about creativity. Supervised learning is just like repetitive stuff, you know. You have a model that you can use for different problems. You just have to pre-process it. So
Running a stochastic gradient with a sim. Why is stochastic?
yeah, it does. So there are some like things called ADAM optimizer. So I don't really delve further into the optimizers because like I always use like similar ones because I'm content with them. But like basically the optimizer you use also changes your accuracy, of course. So that was basically the workshop. If you want to leave, you can leave, and I will send you the like solutions for the project. You can find it on our GitHub, and you guys have our GitHub, right? I showed you that. If you take that six-hour course, but if you watch it like very carefully, you can be proficient. Like you can build something within a day. It's all about ambition. Guys, make sure to start our project. Yeah, we need some stars. We need some directions. So I will upload the solutions to here under workshop 4 folder. Yeah, you can find the solutions here. I will post it. And I will post to YouTube as well, YouTube link as well when I upload the video. Are you guys all in our Discord channel? Yeah. Okay.
You post the GitHub on the Discord.
Yeah, I can post it there as well. Do you have any other questions? I can end Zoom meeting. People on the Zoom, do you have any other questions? Thank you for your comments.
Three. Well, then there would be a case where one layer is better than 3. Like, there's like a little more layers, and that would be a bad thing.
Yeah, because like usually they are good things, but like let's say because of more layers, you have less time to train. Then of course one layer might be better than. But if you train enough for each layer, then more layers would lead to higher accuracy in training sets, but you might face overfitting problems. So I will end the Zoom record. Thank you all for coming. It was a pleasure.